Hey everybody, here we go with lecture 26, getting down to the end of the course, huh? 26, 27, 28, and 29, and that's the last lecture, so we're getting there. Then the focus will be on doing a really good job on that final project paper, and I'll be working with you on that as well. So here goes. Here's here's a fundamental law from Physics 111, specialized for the case of an EM wave which travels at the speed of light. You know that for any wave phenomena, velocity is frequency times lambda. So yes, that's true. But for this particular case, with the velocity equal to the speed of light, c equals f times lambda. So the correct answer is this one here. B was almost okay. Remember where this one comes from, huh? You can write this one as lambda equals velocity over the frequency. Frequency is 1 over the period, so that's equal to velocity times the period of the wave. So the interpretation is distance equals velocity times time, huh? So the wave travels one wavelength at velocity v in a time t. Velocity in this particular case for a speed of light is that quantity there. Number 2, energy in an EM wave is described by the Poynting vector. Yes, that's true. It's perpendicular. That energy is carried in a direction which is perpendicular to E and B, but it is in fact a scalar quantity. So S is 1 over mu naught E cross B. This is a vector that points perpendicular to both E and B. If E is here and B is here, the Poynting vector goes that way. E is perpendicular to B, it's perpendicular to S, and it's perpendicular, and B is also perpendicular to S. So these are a mutually orthogonal pair, a triad of vectors. Okay, so all of that is true. Okay, now I got a bunch of crossed out pages here. I threw this together the last day that I could go on campus back in March, whatever that was, March 21st. So I threw quickly together the lecture notes and I scanned them to save time on the department scanner. So there's material here that's just not applicable to the way I've redefined the syllabus now. So this page just doesn't make sense. This page is not in your PDF. I usually just talk about it just kind of in class in an informal sort of way. There's not much substance here of technical stuff, except there's one thing I really want to draw your attention to, and is this figure down here. Do I dare zoom in on that? I'm going to zoom in on that at the risk of messing up later stuff. So here's the EM spectrum, electromagnetic spectrum, starting from 60 hertz here, which is line voltage AC, all the way up to gamma rays. Huh? Everything here, 10 to the third, second, 10 to the fourth, 6, 8, up to 10 to the 20th frequency. This is the frequency down here. This is the wavelength down here. This is every kind of EM wave there is, and that is radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. Those are all just different flavors of an EM wave. Buried inside here, let me do this to save moving. Can you see that? There's, it's not going to focus. That would be more than it's worth. Here's microwaves. Here's AM radio down here. TV broadcast stations, although most people get their TV from cable now. Here's FM radio. Cell phones are up here. Satellite TV. Microwave ovens are in here. Visible light is this tiny little sliver in here. Huh? Infrared below, ultraviolet above. You know a lot of stuff about a lot of stuff if you understand what that spectrum looks like. Okay, so this page is 31.5, which is also not in the syllabus. So you can put a big red X through that one, 31.5. The next page also. Here's the Poynting vector, which is the first of the new material in this lecture. Poynting vector tells us how you transport energy in an EM wave. And the idea is I have an EM wave here, an E and a B, E field and a B field, at right angles to each other, and it's propagating that wave with a wavelength lambda. So that wave enters a slab of material. What's the slab of material? It's a vacuum, or it's some real material, or it's a human body. It's anything. Okay, we might worry about microwave absorption and radiation from gamma rays and X-rays. That would be human tissue. We'd want to know how much energy is absorbed in that tissue, because it can do genetic damage at the cellular level. The way you describe that is with the Poynting vector. Okay, we have energy coming in here. We know how much that is. It's epsilon 0 E squared energy per unit volume. Okay, it hits a slab of this stuff here. I take a cross-sectional area, area A, a thickness dx. That means this chunk has a volume A times dx. Dx goes like velocity of light times dt. So in an amount of time dt, that much energy goes into that space. The Poynting vector is the energy per unit area per unit time. Okay, so that's energy per unit time is the power per unit area. Okay. Here, so here's little u, which is the volumetric energy density. Here's the total energy. This is energy per unit volume. Okay, I multiply it by the volume to get the total energy. That's u times dv. dv is a times dx. Okay, so du, the energy absorbed, is the energy per unit volume, a times c times dt. Take the dt here, get rid of it here, put it over there. That says du dt, energy per unit time, is mu a times c. Divide by the area. Okay, that's the Poynting vector there, energy per unit time per unit area. That's this really simple result, amazingly simple result. The a cancels. It's just mu times c, mu naught, if it's the vacuum. Another way can write that is, I'm sorry, u, lowercase u. That's c epsilon 0 times e squared. Okay. You can write that other ways. You can write it as E times B from that previous lecture. Goes like that. So I have part of the energy in the electric field, part of the energy in the B field. It wobbles back and forth every half cycle. It's that quantity there. And yes, I'm doing this kind of quickly, folks. Okay, so that's the scalar magnitude, okay, of the energy per time. I can write that in the vector form. I keep the scalar form the same. The magnitude of this is the magnitude of that. Okay, but the S vector then points in the E cross B direction, since E is perpendicular to B, and goes like that. So here's a kind of a summary. Here's a pocket summary of the entire story of the Poynting vector. The Poynting vector gives you the energy per unit area per unit time, power per unit time. Okay, and the direction is perpendicular to E, perpendicular to B, and because we know that E and B are perpendicular, and we take the right-hand rule for the direction of that vector. Skip this homework problem, which referred to the previous syllabus. These two homework problems, which I kind of hope you're doing, even though I know you don't have to study for a test, these are real fundamental problems. Okay, those of you taking MCATs ought to know about this kind of stuff. Okay, here's the most important Poynting vector I can think of these days. It's the solar constant. Okay, how much energy comes from one particular EM wave? It's the EM wave from the sun. Okay, and the solar constant is the energy that falls on a meter square of the Earth's atmosphere per second. That's a Poynting vector. Incident on the far Earth atmosphere, that's about 1350 watts per meter squared. That's 1.35 kilowatts per meter squared. Okay. Remember what that means? Remember power way back in the beginning of the course? Think about what a kilowatt is. A kilowatt is like a hairdryer. Huh? So if I could capture all the energy in a square meter of the Earth with a heating panel or a solar power cell, I would only need 1 square meter to run that kilowatt hairdryer. But that's not the story. This is an incident on the edge of the atmosphere. The atmosphere absorbs a lot of that energy. Okay, on a bad day in Ireland, for example, which is kind of average weather conditions, which are terrible compared to ours, you only get 100 watts In the US, it's kind of like 250, 300 watts per square meter. At this point, I would tell you a long story about my solar array on my roof and talk about that. Sorry, I'm not going to do that, because we need to move on to the beginnings of optics. Okay, and to do the beginnings of optics, we need to talk about reflection and refraction of light. Today we're going to talk just about reflection. Okay, and here's what we're going to do. You can kind of breathe a sigh of relief now, because all this complicated calculus that we talk about for Maxwell's equations get reduced to some real simple ray tracing diagrams. Okay, here's an EM wave from Maxwell's equation, E cross B in a K vector. And we're going to reduce all of that to a picture that looks like this. Okay, here's an EM wave that travels, a light wave that travels from an object. It's a mirror surface or a concave mirror, or goes through a lens, and it reflects back to the eye, and we see an image. We get rid of the E field, we get rid of the B field, we get rid of the wavelength of the K vector. We say that that wave comes in. Here's an incident ray striking a mirror, and then that mirror reflects the ray somehow. Okay, so it's a ray tracing diagram. The law of specular reflection says that if I have an incident ray on a mirror, then the angle that it makes with respect to the perpendicular is exactly the same as the reflected ray. I kind of said that backwards. Here's the incoming, here's the outgoing. This angle of the reflected ray equals that. Okay, that's for a perfect smooth surface. If you have optical roughness, a wavy surface or scratches in the mirror, then you get blurred images. Okay, but you can read the textbook for that. We want to know how to form images with optical elements. Okay, and there are going to be two types of images: a real image and a virtual image. This is where I really wish we were in class, because I could demonstrate to you what a real image is and what a virtual image is. Okay, here's a kind of an operational definition. A real image can be projected on a surface. A virtual image can't be projected. Let me show you how you form the image in a mirror. Okay, a plane mirror. Here is a mirror sitting here. Maybe you've got a full-length mirror in your bedroom somewhere in your house. Okay, and you look at something. It's in front of you here, and here's the mirror. Okay, so let me tell you how to read. Let me tell you how you read these images. First of all, you follow the areas from the object to the eye. Okay, we tend to be anthropocentric, egocentric. Okay, we want to start from the eye. Well, start from the object. Okay. So here's a point on an object on the top and a point on the bottom. Okay, I take a ray from the object here that goes this way, arrow's going that way. It hits this surface here, reflects, and it hits your eye there. I take another little ray that goes a little bit lower down, and that strikes the object there. Okay. Those two rays are diverging on this side of the mirror, but if I extend them back to this side here, they converge at a point behind the mirror. Okay. Do the same thing on the bottom. Okay. Those two diverging rays over here converge back to here. So this system makes an image, a virtual image that looks to be back here. Okay. It has, for this particular case, that image is exactly the same distance behind the mirror as the object is in front. Okay, and it has the following properties: it's upright, it has the same size as the image, and it's a virtual image. Okay, I can't project that image on a screen. Okay, I'll show you an example later on when you can. Okay, so I said a word about that. Okay, here's an example. Okay, here's an example, which is example 33-8, and it's seeing yourself in a mirror. Okay, and the question is, how tall must a full-length mirror be to see yourself? Well, the answer is kind of interesting. It doesn't have to be as big as you are. It only has to be exactly half as big as you are. Okay, and here's that proof. Okay, I take the toe down here, reflect that way, it goes to an image down here. I take the top of your head here, and it makes an image back there. Okay, that distance is half as much. That's a real rushed explanation of that. Okay. Okay. What do I want to say about that? I don't want to say much more about that because next time we really get into lenses and mirrors. Okay. There are 3 homework problems here which are really valuable if we had time to spend going over them. If those of you who are doing GREs or going on to grad school, I suggest these 3 problems that you look at. For the rest of you, spend more time on these ray tracing elements in the book and try to get a feeling for them. This is again where a lab will be really helpful. This will be the last lecture that I post before Easter break, Thanksgiving. I'm going to post another Zoom meeting online for the Wednesday before Easter break. In the meantime, take care of yourself, stay healthy, take care of everyone around you. Adios, you guys.